My presentation is about numerical modeling of brittle fracture using a phase field approach, and my talk mainly deals about the constitutive assumptions in the phase field. Here's a brief outline of my talk. So first I will give a short overview of the phase field model for brittle fracture. Then I will show different possibilities to include different constitutive assumptions in the phase field approach and in a variationally consistent framework. And this leads to some problems concerning crack boundary conditions and to restrictions on damage modeling. By the cost of giving up this variational framework, we can include physically motivated crack boundary conditions, including contact, and phase field evolution equations. And finally, there will be numerical examples. So in the phase field approach for fracture, the sharp crack is approximated by a smooth functional. This avoids jumps in the displacement field and the corresponding numerical difficulties. Accordingly, the surface energy of a sharp crack can be replaced by a surface energy density, and the hereby introduced additional scalar field S, the phase field, describes the state of material between S equal to 1 for intact material and S equal to 0 for fully degraded material, while length parameter L controls the width of the transition zone between both states. Here you see the corresponding Lagrangian, including terms of the kinetic energy, the elastic energy, the crack surface energy density, and external work. In order to obtain the partial differential equations for dynamic brittle fracture, we employ Hammond's principle, and variation with respect to the unknown displacement field and phase field finally gives the coupled set of partial differential equations, the momentum balance equation, the evolution equation, and the corresponding boundary conditions. The elastic energy density can be decomposed into two parts. One part is degraded by degradation function g. This part here is called active, and the other part only depends on the strain. This part is called passive. The sum of both parts is equal to the linear elastic energy in the undamaged state. There are several possibilities to construct this degradation function, which has to fulfill some general requirements. A very common choice is the quadratic degradation function, and as it can be seen on the right hand side in the simple example of a tensile bar, a large amount of stiffness is lost before failure occurs with the second order degradation function, and this is not typical for brittle materials. Therefore, the choice of a higher order degradation function is more suitable. However, we propose a slight modification by taking an additional requirement into account with a small parameter A1 in order to circumvent numerical difficulties. In order to take the different behavior of cracks under compression into account, two approaches are well established. The spectral decomposition, in which only the positive principal strains are in the active part, and the volumetric deviatoric split, in which a positive volume change and distortion deliver energy to the active part. Variationally consistent treatment directly provides the phase field evolution equation, where the split prevents damage under compression, as well as the stress tensor, where the split introduces a contact condition in order to prevent interpenetration of material. Before I discuss these two models, I would like to show you the numerical treatment and introduce additional constraints. In order to solve the coupled set of partial differential equations, we employ a standard finite element implementation here shown by means of the element residual vector. To prevent crack healing, a Dirichlet boundary condition is imposed where the material is fully broken. Alternatively, if we use the phase field to describe damage, a non-negative damage rate can be enforced by replacing the crack driving energy Ds by a history field, which includes the maximum crack driving energy obtained in history. Making use of such an history field is an elegant opportunity to model initial cracks, as it can be seen on the right side. The initial crack can also be modeled by directly constraining the phase field to S equal to 0. As already mentioned, the choice of the energetic split directly controls the energy contribution in the phase field evolution equation as well as the non-interpenetration condition. This is rather restrictive regarding the formulation of different damage and failure criteria, and lead to some problems as it is shown here by means of 2 examples. We use such a through crack plate subjected to horizontal displacements, and the initial crack is modeled by the phase field as shown before. The state of fully degraded material should reproduce the behavior of a macroscopic crack. And using here now the spectral decomposition leads to a stiff elastic response, which is shown here by means of a deformed mesh and by significant reaction forces. And with further loading, unphysical fracture pattern occurs. In a second example, we test the tension compression asymmetric material response of a bar using the volumetric derivatoric split. The compressive strength is not much larger than the tensile strength. And so these 2 examples show the limitations or the problems concerning with this variationally consistent treatment. In the following, we give up this structure to some extent in order to incorporate physically motivated crack boundary condition and phase field evolution equations. The aforementioned approaches have in common that they do describe isotropic damage without taking the crack orientation into account. In order to include the directional dependent properties of a frictionless crack, which means that the positive normal stresses as well as the shear stresses should vanish, we propose 2 approaches here. They are formulated in a coordinate system aligned with the crack normal. The crack normal vector can be computed from the gradient of the phase field. In the simple unilateral normal contact model, only negative normal strains lead to an elastic response, while the stiffness in crack parallel direction is reduced by the phase field. The second model is more sophisticated, however in better agreement with continuum mechanics. Here you should note that the stiffness in crack parallel direction is also influenced by the phase field, however it's not fully degraded. To compare both approaches, we use the simple test of a through crack block subjected to compression normal to the crack direction. Not taking the crack orientation into account leads to significant problems in reproducing the homogeneous stress response. Using the simple unilateral normal contact model, or the simple unilateral normal contact model cannot accurately reproduce this homogeneous response. However, the error is sufficiently small for small process ratios of brittle materials. I'm sorry that you cannot read the values, but you have to believe me, here the error is small compared to this example. The second model can accurately reproduce this homogeneous response or in perfect agreement with the analytical results. Using again this shear test here demonstrates the good performance of the crack orientation dependent degradation in the phase field model, here shown by means of the deformed mesh. So we see the 2 parts sliding on each other, and the small remaining shear stress in this model is due to the regularized formulation of the crack. In addition to an appropriate stress response, we need a constitutive assumption to model the phase field evolution, and here are some of the possibilities. We have strain-based criteria, for example, where only the positive principal strains are in this crack driving energy term. By introducing an energetic threshold value, we can reduce the stiffness which is lost before failure occurs. Similar stress-based criteria can be formulated by a Legendre transformation, and finally there are attempts to formulate pure stress-based criteria. Due to lack of time, I will skip the following slides. The important point here is to show you that evolution equations based on the strains or the energetic threshold show almost mesh-independent results. Only one curve here, the red curve, is different due to the poor approximation of the phase field. In contrast, the phase field evolution criterion based on the pure stresses is very mesh sensitive. So that does not work. I will also skip this benchmark and will continue with this non-standard problem of fracture mechanics and indentation fracture problem here under plane strain conditions. A flat rigid punch is pressed against a flat surface block of brittle material, and an initial crack occurs some distance outside of the frictionless contact zone, and this happens spontaneously. The important point here is that the initial crack starts from a defect-free surface, so it's the position of this initial crack is not triggered somehow. The phase field method seems to be well suited since it takes the strength and the toughness into account, and in addition the method does not require any assumptions concerning the unknown location of the crack paths. By using this here shown crack driving energy term, including this energetic threshold value, the simulation qualitatively can reproduce the different stages of the indentation fracture problem, which means that at the beginning no crack occurs. By exceeding a critical load, an initial crack of a finite length starts some distance outside of the indenter, almost perpendicular to the free surface, and with further loading the crack evolves on an almost constant angle. Okay. To sum up, I showed the implementation of a phase field approach for brittle fracture. I discussed some problems concerning the tension compression asymmetric response, if we treat it in the variationally consistent framework. We proposed some physically motivated models concerning the crack boundary conditions and the phase field evolution laws to achieve better or more realistic results, and there's still much work left. We try to improve the numerical treatment of our proposed models, as well as we will quantitatively compare the different phase field evolution laws and validate them. With this, I would like to conclude and thank you for your attention, and I'm looking forward to answer your questions. Thank you.